In this subsection, we'll try to summarize how the LDA is applied for dimensionality reduction. For the theta metric X, we consider the points are stacked vertically so that each row represents a sample. Here we have main steps for the LDA used for dimensionality reduction. First, we standardize the data set, and for each class, and we compute the mean vector, and we construct the within class scatter metric and between class scatter metric. And for the metric, SW inverse and SB, we try to get eigenvectors and eigenvalues. Of course, we have to sort the eigenvalues by decreasing order, and we try to choose the k eigenvectors corresponding to the k largest eigenvalues. Now, for eigenvalues and eigenvectors, we have c-1 eigenvalues and eigenvectors. Among them, we try to choose k eigenvectors, and then we can get a truncated transformation metric, and k must be larger than or equal to c-1. Now we project the samples onto the new feature subspace. That's now because we start with transpose of X, so that now rather than, and earlier we considered this projection W transpose X. Now we are using transpose of that so that we can write in this way. That is the projected samples. Okay, here we have a remark. Rank of the metric is now less than or equal to c-1. So we have to choose k not larger than c-1. And the projected feature and ij component of z is the same as that one. Ith data point and jth projection vector. That is in the projected coordinates. And if you consider the original coordinates, then you multiply here now wj. Okay. Now the LDA has limitations. LDA produces at the most c-1 feature the components, so that if you need more than that, then you have to use other method to get additional features. And LDA is a parametric method because it assumes unimodal Gaussian likelihood. That means that the method assumes that each class, the points are distributed in Gaussian distribution, and also the single Gaussian model. And so that is unimodal Gaussian likelihood. If the distributions are significantly non-Gaussian, then the LDA projections will not preserve any complex structure of the data. And here, LDA will fail when discriminatory information is not in the mean, because it's a mean-based algorithm. In many algorithms, in classification, many algorithms are mean-based. And if the information is not in the mean, then the LDA will fail. And sometimes the discriminatory information is in the variance of data. So geometric shape is sometimes more important than the class mean. So that once it is happening, then LDA will fail. Okay, here we have a comparison between LDA and PCA. Such example is often used in machine learning classes, machine learning lectures. Here, for these data points having two classes, if you are using PCA, then now PCA main direction is this one, so that once you try to project the points, then everything is messed up. Because PCA is working without using any labels, so that is happening. Now for LDA, now here after projection, you have really good discriminatory information, and then here is well separated. So that sometimes people are saying that LDA is much better than PCA, but it's not really true. In fact, the PCA is working without using any labels. But anyway, for the LDA, if you don't have any label in the beginning, then even you cannot start with the LDA. Okay, so that if we see such comparison, then it's not really a fair comparison. Anyway, here Fisher's LDA was generalized under the assumptions of equal class covariances and normally distributed classes, and it's a center-based algorithm. However, even if one or more of those assumptions are slightly violated, the LDA for dimensionality reduction can still work reasonably well. So it's a really good algorithm. But here, such comparison is not really fair. The PCA is really wonderful algorithm. And if you can develop some PCA or is a variant using labels, then you can do really also very good result. Okay, that's the end of the section. Thank you.